Hello and welcome to This Old Lab. Today in this episode we're going to be talking about the scientific method. It's a systematic approach that we use whenever we engage in scientific activity. And to do that, we're going to build some houses in the name of science. Stick around. Whether it's the study of biology, or the study of physics, or the study of chemistry, we always use the scientific method when we engage in that scientific study. The scientific method is a set of steps, an organized pattern that we use to give us consistency in our study. If we have one scientist who studies a subject, and he or she comes up with a particular set of conclusions regarding that subject, it's important that another scientist can go through the same consistent process to be able to verify or to counter the conclusions of the first scientist. You get it? We have an even playing field with the scientific method. So what kind of things are involved in the scientific method? Well, we might actually start with an observation. An observation is simply the act of gathering information. Generally speaking, we divide data into two categories. We can call it qualitative. Qualitative usually deals with our senses: sight, sound, taste, touch. I would say that this board is a tan color. That'd be an example of a qualitative observation. On the other hand, quantitative data has to do with things like length or mass or volume. Amounts, right? Quantity, quantitative. I can take this tape measure and I can measure the length of the board, and it's around 66 inches. That would be an example of quantitative data. After gathering that information, we might actually come up with a hypothesis. A hypothesis is a tentative explanation for the things that we've observed. Now, tentative in the sense that I'm not absolutely certain of why or the reasons for what I've observed, but maybe I have a pretty good idea. But then we have to know whether our hypothesis is valid or not. That's where experimentation comes into play. An experiment, a set of controlled observations that will either support or counter my hypothesis. I may be able to confirm my hypothesis in what I see in my experiment, or I may have to tweak my hypothesis a little bit afterwards. Now we'll get to more about experiments in just a minute when we build our houses. And those experiments might give us a large amount of data, so it's going to be important for us to be able to take that data, analyze it, to check our hypothesis and see whether it's confirmed or countered with that data. In doing so, we'll form a conclusion, a judgment based on the information that we obtained in our experiment. Now, it's important to note, a hypothesis is never really proven. What we do is we see if the data supports the hypothesis or not. It may be that the hypothesis is mostly true, but it may need a few changes here or there as we continue to experiment through the years. But over time it may be that observations are seen that may discount or disprove that hypothesis, and then it needs to be changed or altered. Now we might actually get to the point where we can establish a theory. A theory is an explanation of a natural phenomenon based on many observations and investigations over time. Now the key there is observation, being able to observe these things happening. So if we can't observe something happening, what does that say about the theory itself? If something cannot be reproduced, especially reproduced often, then how can we truly call something a theory? Side point. That calls into question the idea of what we call macroevolution a little bit. While we absolutely have seen examples of microevolution, adaptation, survival of the fittest, and so forth, what we've never seen is an organism going from one family to another, or one order to another. We don't see that. So therefore, can we really say that macroevolution is a valid theory? We need to be able to observe these things happening in order for that theory to be valid. You may have heard of Einstein's theory of relativity. Now that's a theory that's really stood the test of time. It's a great example of a successful theory in that it can be used to make predictions that are true. Now we might observe something that we see in nature, a relationship, for example, and we find that there are no exceptions to that relationship. Let's say I'm working with this tape measure and I'm a little lazy. I want to put it right here so I can reach it better. I don't want to put it on the ground because then I'll have to bend over and get it. So I try to just place it right here. That didn't work. So maybe I try it again. I'm going to set it right here so that I can come back to it and get it when I need it. Now, hopefully, it wouldn't take me too long to understand that there's a relationship there. And then I might ask the question, well, is it just the tape measure? Does it happen with other things? Can I take my hat, for example, and do the same thing? Yes, of course I can. What I would find is, over the course of many observations and experimentations, is that everything on this earth is pulled toward the center of the earth. That's what we call universal gravitation. Gravitation is an example of a scientific law. A scientific law is a relationship in nature that's supported by many, many experiments. Now, something else you should know. We don't have to take the same exact order with these different steps in the scientific method. In fact, we may have a hypothesis first and then observe something. Or we might have to go back and change our hypothesis after experimentation. You get the idea. What is important, though, is that these different aspects of the scientific method are used. But now comes the fun part. It's time to build some houses. So give me just a little bit and I'll be right with you. I didn't say they were going to be full size, now did I? So this is my experiment. An experiment is a set of controlled observations that test my hypothesis. Now my hypothesis in this case is, I believe that the color of my house can affect how much electricity I use in the summertime. All three of these houses, as you can see, are identical, except for one thing. That's right, the color. Now, that one thing, that variable that I plan to change in my experiment is called the independent variable. I've also placed a thermometer in each one of these houses. Those thermometers are also identical. I even tested the three of them to make sure that they measure in the same exact way. I'm keeping everything the same except for that one variable, the independent variable. I'm going to let these houses sit in the sun for a while. The same location, same environment, and afterwards I'm going to check the temperature inside each one. Now the changes that occur in response to the independent variable, the thing that I change, is called the dependent variable. In this case, the temperature should be my dependent variable. How will it change based on the color of the house? One more thing. You can also see I have a gray house here in addition to a black and white house. That gray house is going to represent my control. It's going to be my standard for comparison, my baseline to see what effect changing that independent variable has on this experiment. So let's give it a little bit of time, allow it to absorb some heat from the sun, and we'll see what effect that has on the temperature. Okay, we're back. Now, I've put them out in the sun where they can sit for a while, and they've been out here for a few hours. So let's take a look and see what temperatures we have. We'll start with the gray house. Okay, I see a temperature here of 40 degrees Celsius. 40 degrees Celsius, that's about 104 degrees Fahrenheit. Let's check the black house. Interesting. I see 42 degrees Celsius. So it's a whole 2 degrees warmer than the gray house was. Let's try the white house. This is fascinating. The white house has a temperature of 37 degrees. So it's a whole 3 degrees cooler than the gray house was. So we can make a good conclusion here and say that the darker the color, the higher the temperature inside. Probably due to the fact that we have more heat energy being absorbed by the darker colors than we do the lighter ones. So the darker colors will have higher heat inside, which means my air conditioner is going to have to work harder, isn't it? And in the summertime, a harder working air conditioner means a higher amount of electricity, which means a higher electric bill. Hey, that's all the time we have for today. I hope it's been informative for you. Today we talked about the scientific method, the different aspects that we use when we have a scientific study. We talked about observations, the act of gathering information. We talked about a hypothesis, that tentative explanation for the observations we've made. Then we talked about experimentation, how we have a set of controlled observations that help us to establish whether or not our hypothesis is true. We also talked about different types of variables. The independent variable, the thing that we change in the experiment. And by the way, if we were to graph that information, the independent variable would be on the x-axis. The dependent variable is what happens as a result of what we've done in our independent variable. And on a graph, that would be our y-axis. We also talked about a control, a baseline for comparison, and then we talked about making a conclusion after we've had many observations in our experiment, being able to establish whether it makes our hypothesis true or whether it needs to be changed. Finally, we described the concepts of a theory and a scientific law. Again, I hope this has been helpful to you. And if you have any questions at all, please don't hesitate to contact me. All right, have a great day and God bless.